In this video, we will see about the operation, output voltage expression, critical inductance and output voltage ripple calculation for a boost converter. What is a boost converter? It is a DC-DC converter in which the output voltage is greater than the input voltage. So if I give a voltage of Vs, I always get a voltage greater than the given input voltage. So it is called a step up converter or boost converter. The main applications of a boost converter are solar PV system, electric vehicles, LED drivers. Let us see the circuit diagram of the boost converter. This is the input side, which includes the input source voltage, and this is output side, which consists of a resistive load, and a capacitor is normally connected in parallel with the load to reduce the load voltage ripple. And the circuit essentially consists of three components: an inductor, switch and a diode. So by changing the position of these switches, we can get different configurations of DC-DC converter. You can remember the buck converter, which consists of these three components, whereas this switch will be placed in series with the source, and inductor will be connected at the output side, and diode here. It will be connected as a freewheeling diode. So by changing these three components, you can get different configuration of DC-DC converter. For boost converter, that is, you want to boost the output voltage, an inductor should always be in series with the source voltage. This helps to get the output voltage greater than the source voltage. And duty cycle, we know D is equal to T on by T. So I can write T on as dt and T off as 1 minus D into T. Considering the on condition of this switch, when this switch is closed, the current flows to the inductor switch and back to the supply. So the inductor current increases linearly. So the voltage is also positive because VL is equal to L into di by dt, and di by dt has a positive slope. So we can write the equation. Vs minus VL is equal to 0. So VL equal to Vs. In this case, this diode remains reverse biased and the load current is supplied by the capacitor current. The capacitor discharges to supply the load current. And writing the KCL at this junction, since the diode current is 0, only two currents are there, IC plus I0 equal to 0. IC is equal to minus I0. Now considering the off condition, the inductor current continues to flow through the diode and the load and back to the supply. Now writing down the KVL, Vs minus VL minus V0 is equal to 0. From that you can find what is the inductor voltage. And at this junction, there are three currents because diode is conducting. So what is diode current? That is nothing but the inductor current IL, because same current is flowing here because the switch is open here. So inductor current is equal to diode current, and that is split into two, IC plus I0, and the capacitor will be in charging mode. IL is equal to IC plus I0, so you will get what is IC. You can see that in both the cases, the source current is continuous. That is, in this on condition, current flows from the source. In off condition also, current flows. So the source current is continuous in both the cases. Now we will derive the voltage second balance equation, that is voltage into time period equation for inductor voltage. So during on condition we have derived the condition VL is equal to Vs, and similarly for off condition also we have already derived what is VL. Now in steady state, the average inductor voltage is always 0. So, this voltage, on period voltage into on time plus off period voltage, this voltage into off period is equal to 0. So, substitute the values, you will get V0 is equal to Vs divided by 1 minus t. Now, if you substitute d equal to 0, we will get V0 equal to Vs. And when, for example, when Vs is equal to 100 volts, you can see that D equal to 0.1, V0 is 111 volts, and D equal to 0.5, V0 equal to 200 volts, double the supply voltage. So we can see that always the voltage is higher than the supply voltage. The output voltage is always higher than the supply voltage. It is called a step up converter. Now you may get a doubt, what happens when D is equal to 1? So you substitute 1 here, 1 minus 1 is 0, so you will get infinite. But practically you will not get infinite voltage because the inductor has some internal resistance. So because of that there will be losses and you cannot boost up the voltage beyond a limit. So this boost converter will work for lower duty cycle, whereas at higher duty cycles its performance decreases. You can see from this waveform, this is normalized voltage. It means that V0 by Vs. Okay, so V0 by Vs, and this is duty cycle D. See this blue color waveform. This one is the ideal inductor. That is, there is no internal resistance. In that case, it goes to infinite value. Your output voltage may go to infinite value. But if it is a real inductor, that is in practical circuits, it has some resistance, internal resistance, which decreases the voltage after a certain point. So in boost converter, you can see that when you operate the boost converter at low duty cycles, it may perform well. But the same converter, when you operate at a higher duty cycle, you can see that though you increase the duty cycle, voltage reduces. This is how a practical circuit will behave. This is mainly due to the presence of internal resistance in the inductor. So inductor design plays a major role in the performance of boost converter. Next we will derive the ampere second balance equation. So ampere means current into time period. For capacitor current we can derive the equation. So switch on condition, switch off condition, this current into on time, this current into off time equal to 0. So you will get IL is equal to I0 divided by 1 minus t. So there is a relation between the inductor current and the output current. Now we will calculate the inductor current ripple. So this is inductor voltage on time and off time. So we can see that the inductor current increases linearly during the on time and decreases during the off time. And this IL average, and this is called the ripple. This point to this point, blue color, this one is called del IL or the current ripple. Now we are going to find what is this del IL. So in on condition, you can take on condition or off condition, whichever is convenient for you. I have taken on condition. So VL is equal to Vs. In on condition, VL is equal to Vs. So what is VL? L into di by dt. So di by dt I am writing as di as del IL divided by on time period is dt. So this is T on period, that is equal to Vs. So from this you can find what is del IL. So del IL you will get this one. Instead of T you can write it as 1 by F, because we will talk about frequency only when we design inductor. So we used to specify it as F, 1 by F, T is equal to 1 by F. So current ripple is equal to dVs divided by FL, or ripple is inversely proportional to the inductance. So if you increase the inductance you can reduce the ripple, and it is always desired to have a low ripple in the inductor current waveform. Next, we will calculate the critical inductance. What is critical inductance? It is the minimum value of inductance at which the inductor current just touches zero and goes up. If I have an inductance greater than the critical inductance, the converter will be in continuous conduction mode. And if I have an inductance less than the critical inductance, converter will go into discontinuous conduction mode. So at boundary condition, this is the inductor current, and if I find the average value of this IL average, that will be equal to del IL by 2. So the total ripple is del IL, half of that, that is the average of this is del IL by 2. So I write IL is equal to del IL by 2. But already we have derived for the current ripple del IL. So take that equation. So del IL I can write dVs by FL. 2 I have taken. What is IL? I naught divided by 1 minus T. This we have got from capacitor ampere second equation. So find what is L. That L is called the critical inductance. So L is equal to R into D into 1 minus D the whole square divided by 2F. So inductance is inversely proportional to F. So if you increase the switching frequency, inductance will reduce. And D into 1 minus D. So this critical inductance is always a function of load as well as duty cycle, because at one particular duty cycle you will get this critical inductance. Next, let us take the calculate the output voltage ripple. So this ripple is controlled by the capacitor. The charge on the capacitor can be given by Q is equal to C into V. What is the charge on the capacitor? Take the capacitor waveform. This capacitor waveform, you can see the on period it is of rectangular shape. What is the area of the rectangle? Length into breadth. So this is time period T on. So that is equal to dt, and height is I naught. So I naught into dt is equal to this one. From this you calculate what is this. That is I naught can be written as V naught by R. So output voltage ripple is equal to this one, and output voltage ripple is also inversely proportional to frequency as well as R and C components. So the points to remember here are boost converter is also called a step up converter because the output voltage is always greater than the supply voltage. Output voltage is equal to Vs divided by 1 minus D. But you cannot have a very high value of D due to the internal resistance of the inductor. We cannot increase the inductance too much, because of that as we increase the inductance too much, internal losses I square R losses will be more. And frequency plays an important role in the selection of core of inductor, because if you use an iron core and if you increase the frequency, hysteresis loss will be more. So inductor design is very important in case of a boost converter design. If you like the video, do subscribe to our channel, and if you need the study material, you can visit this website. Thank you. These are some of the references.